In this video we're going to look at dry convection and dust devils. An example of a dust devil is shown in the top right picture. A dust devil is a rotating column, a rapidly rotating column of suspended particulate matter that occurs in a hot environment. And dry convection is a convection that occurs where saturation is not reached. So there's no condensation level. What's shown here is a map of Africa and Oceania, and in particular I want you to look at the desert and semi-desert regions. These are arid regions with high surface albedo, cloud-free, intense shortwave radiation and large surface temperatures. They're also arid because there's very little moisture about. These dry regions see the formation of dust devils, or PO, and dry convection. And it's common to see super adiabatic lapse rates at the surface in these areas. So a super adiabatic lapse rate is a lapse rate that's greater than the adiabatic one of 10 degrees Celsius per kilometre, and it's caused by intense solar heating at the surface. So remember, a dry adiabatic lapse rate is established by heating the surface and then convecting up that heat. So a super adiabatic lapse rate will form when there's a dry surface, so there's none of the shortwave energy is going into evaporation, and where there's light winds, so there's inefficient mixing of the hotter air right at the surface upwards to establish the dry adiabatic lapse rate. So the heat can't mix through a deep layer rapidly enough, which is confined to a shallow layer near the surface, and this results in vigorous convection. And in this region, dust devils can form. So just like the ballerina, if you have some rotation in the low-level wind field, if you stretch it out via deep convection, you get a rapidly rotating updraft. Just like the ballerina pulls her arms in and spins more rapidly, it's the same effect. And this means often that you're going to get a maximum temperature that's 1 or 2 degrees warmer than if you had simply a dry adiabat from the surface upwards. Here's an example from Cobar in central New South Wales, and you can see from the mean sea level pressure chart, the pressure gradient is weak, and it's a light northerly drift as a result. From the temperature profile, you can see an approximate dry adiabat to about 10,000 feet, and the potential to mix thermally up to about 600 hectopascals, or 14,000 feet. Finally, you should be able to see the super adiabatic lapse rate in that profile as well. And we can note in passing that the lower part of the dew point profile is also well mixed, being approximated by an isopleth of mixing ratio. So this is a prime candidate for dry convection because there's clearly no condensation level for this trace, and also for dust devils. So for this particular day, the area forecast carried the following: moderate turbulence in thermals below 9,000 feet. So it's moderate in strength. Thermals refer to the dry convective motion. 9,000 feet is the top of the well-mixed layer, that turbulent layer due to heating. And the tilt 10Z is till the sun goes down, and the heating dies off at that point. And mostly in the west is just telling you where temperatures are sufficiently warm. At the bottom there is a Cobar TAF, and there's a few things worth noting. Firstly, from O2, dust devils are initiated and some scattered cloud as well. Dust devil indicated by the PO. At the same time from O2, moderate turbulence below 5,000 feet until 08. So the cooling will begin at sunset, and the 5,000 feet is lower than the value that you'd put on the area forecast, because for a TAF you're only interested about conditions to 5,000 feet. And then finally, look at the temperatures. They're starting from 19 UTC, so the 33 and 36 indicate that you really want mid to high 30s before dust devils and dry turbulence occurs. So here's some quote-unquote rules for dry convection and dust devils. Firstly, you want the maximum temperature to be expected in the high 30s, sufficiently warm. You want the convective temperature to be greater than the maximum temperature, which means that there's no condensation level, and so no clouds form. The planetary boundary layer, remember, is the depth through which you have this dry turbulent motion happening, and if it's deep, then for the area you'll forecast mod turb below x thousand feet, where x is the depth of the dry adiabatic layer. You can also forecast dust devils, PO, on the area. For particular TAFs, you'll have PO on the TAF, and if there's no cloud, then you'll write it as follows: 9099 indicates 10 kilometres visibility, PO, and then SKC means sky clear. This will occur from about 01 to 02, which is 12 to 1 Eastern Daylight Savings Time, which is the time of about maximum heating of the surface. Not the time of maximum temperature, but the time of maximum heating. And for really hot days or weak radiation inversion, you can even begin at 11 a.m. 00 UTC for Daylight Savings Time. And the till is anywhere between 8 and 10 Z when radiative cooling begins. Here's an example. This is Alice Springs. Is this trace a candidate for PO? For dust devils? Well, consider the location, consider the season, and have a look at the features of the trace. Write in TAF format for the 02 to 14 period the mean weather line. So ask yourself, will there be cloud? Any precipitation? What's the elements of concern? And the wind. And also a turbulence comment if appropriate. You might want to go back in the handouts and look at previous examples of TAFs for this particular phenomena. Just a note for the wind, remember that parcels bring down their horizontal momentum in mixing. So if there are stronger winds aloft and you have thermal mixing, then you'll bring down those wind speeds. So pause this video now and have a crack at this exercise. Well, how did you go? We'll say yes to dust devils because it's Alice Springs, which is in Central Australia and is arid, and it's summertime. Moisture mixed to 550 hectopascals, a dry adiabatic lapse rate to 650 hectopascals, so it's all consistent with a well thermally mixed environment, and so one would expect moderate turbulence. There's about 15 knots from 40 degrees at the surface, and we're likely to mix down 20 knots as gusts in the afternoon. Is there cloud likely at 550 hectopascals? Well, at best it's only going to be scattered at 160, so it's not really a concern. So I suggested TAF then is the wind at 40 degrees with the 15 knot wind speed, 10 kilometres or greater of visibility, so 9999, and dust devils. Remember the TAF begins at 02, and it's likely that the temperatures will be sufficient for dust devils and dry convective motions at that time. And we'll mention the scattered 160. From 08, we've got a CAV OK, because we're not really interested in cloud above 5,000 feet on a TAF. And because you're starting to get a radiation inversion, we'll keep the wind direction, but the wind speed will start to lighten off. As you start to decouple what's happening at 10 metres from what's happening further aloft, remember friction will take over, and you won't have that momentum coming down to replenish the wind speed, or replenish the momentum. From 02, mod turb below 14,000 feet, well, that's speaking about what's happening in the environment. Really, that's not what you'd put on a TAF because you're only interested to 5,000 feet. But that's going to represent the depth of the mixed layer. And that's till 08Z as we form the radiation inversion. To finish off this video, here's an example where there was a dust devil in an outer suburb of Melbourne, which is rather unusual. So the 28th of January 2009, there's the trace. And you can see it's a very hot day. The maximum temperature was 43 degrees Celsius. And there's a dry adiabat, that's a 11Z trace, so there's a radiation inversion. But above that, a dry adiabat all the way up to 1,900, 800, 700, 600 hectopascals, 14,000 feet. An iron shed was lifted off its foundations in Hughesdale and hurled into the power lines. Witnesses reported seeing a 4-metre dusty whirlwind race across the ground, launching the shed over an adjoining property and crashing into power lines. And that is obviously a dust devil. Monash University Professor of Meteorology Michael Reeder said that the phenomena is very common in outback Australia but rarely seen in suburban Melbourne. Well, one wonders whether or not in a warming world, whether or not we'll see dust devils far more often in Melbourne.